And now in this lecture we'll answer two questions. In the first question, we'll find out the radius of this circle, and in the second question, we'll find out the area of this circle using two different methods. So we'll start with the first question. In the drawing, we have a circle. This is the right angle ABC. This is angle ABC. This is right angle. Side AB equals to 3 units in its length. This is line segment AD. That is also equals to 3 units in its length. This is the short line segment DC. That is equals to 1 unit in its length. Again, our task is to find out the radius of this circle. So first of all, we can implement our drawing all 25. All 25 is also defined as second tangent theorem. According to all 25, if from a common extreme point P, this is the common extreme point P, you will draw tangent PA, that is tangent to this circle at point A, and also we have second PC that cuts the circle at 2 points, B and C. So in this drawing, the following equation is true, that PA square equals to PB times PC. Again, PA square equals to PB times PC. So I can actually implement all 25 in our drawing. Why? Because in our drawing, we have, this is the common extreme point P. This is the common extreme point C. From this common extreme point C, we have tangent CE, that is tangent to this circle at this point E. And we have also second CA that cuts the circle at 2 points, D and A. So all the requirements for full 25 are satisfied, and therefore we can implement here all 25. So I write it down. And the common extreme point C. We have tangent CE and second CA that comes the circle at 2 points, D and A. So all the requirements for full 25 are satisfied, and therefore we can implement all 25 in our drawing. According to all 25, the following equation will be true, that CE square equals to CD times CA. And again, according to all 25, the following equation is true. If you focus on the common extreme point C, CE square equals to CD times CA. CE is the missing side, so we leave it as it is. And it is equal to CD times CA. CD is 1 times CA. CA in total equals to 1 plus 3, that is 4. So total, if you want to know that CE square equals to 1 times 4. 1 times 4 is 4, so CE square equals to 4. Here we take a root out of this equation, and you get that CE, the missing tangent CE, is equal to the square root of 4, that is 2. So the length of tangent CE is 2 units. So if you know, if you found out that tangent CE, that is equals to 2 units in its length. In the next step, we will implement the Pythagoras theorem on this right big triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So I copy the right triangle ABC in a new page, and we will implement on this right triangle ABC the Pythagoras theorem. The hypotenuse AC equals to 3 plus 1, that is 4. AB equals to 3, and BC is the missing side. Here by PT is the progression for Pythagoras theorem. So actually, this is the right triangle ABC. Is the code from the original drawing. In this right triangle ABC, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. So I'll write it down. AC squared, that is the square of the hypotenuse, is equal to AB squared plus BC squared. AC is 4, therefore AC squared is 4 squared, that is 16, and it is equals to AB squared. AB is 3, therefore AB squared is 3 squared, that is 9, plus BC squared. BC is the missing side, so we leave this it is. So in total, if you found out that 16 equals to 9 plus BC squared. Here we subtract 9 from this equation, and we get that 16 minus 9 is 7 equals to BC squared. Here we take a root out of this equation, and we get that the missing side BC is equal to the square root of 7 units in its length. This is the missing side BC. Is equals to the square root of 7 units in its length. It is given as the question that point O is the center of the circle. So we join points O and E together by a straight line. Point O is the center of the circle, point E is the point of the circle itself, therefore OE is the radius of this circle. We define the radius of this circle as such, so OE equals to R. The radius OE is equals to R. The radius OE is drawn to point E, that is the point of tendency BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius EO. If BC is perpendicular to EO, it means that this angle equals to 90 degrees. And this angle is equal to 90 degrees according to rule 1. In the next step, we will do another construction. This is to say, from point O, that is the center of this circle, we will draw perpendicular on AB. Again, from point O, we will draw perpendicular on AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AB. This point is point L. By doing this construction, we can do quadrilateral OLBE. Inside quadrilateral OLBE, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral OLBE, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this rectangle plus a square. So we are not quadrilateral OLBE is a rectangle because it has 4 right angles. This is quadrilateral LOBE. It is a rectangle according to rule 5, because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle LOEB, Side OE must be equal to the opposite side LB, but OE is out, therefore the opposite side LB must be also equal to R units in its length. Likewise, according to the same rule, in the same rectangle LOEB, side BE must be equal to side LO. What is the length of side BE? From the drawing it is very easy to see that BE equals to BC minus EC. Again, BC minus EC equals to BE. So, I don't know. We actually found out that the length of the missing 9 segments BE is equal to BC minus EC. So BE in total equals to BC is square root of 7 minus EC is 2. So in total we found out that BE equals to square root of 7 minus 2 units in its length. This is 9 segment BE, this equals to square root of 7 minus 2 units in its length. We continue with the rectangle. Rectangle LOEB. Side BE must be equal to the opposite side LO. But BE equals to the square root of 7 minus 2, therefore the opposite side LO must be also equal to the square root of 7 minus 2 units in its length. So write it down. LO equals to the square root of 7 minus 2 units in its length. What is the length of this missing 9 segment AL? From the drawing it is very easy to see that AL equals to AB minus LB. Again, AB minus LB equals to AL. So write it down. AL equals to AB minus LB. So AL in total equals to AB. AB is 3 according to what is given us the question. Minus LB. LB is out. So in total AL equals to 3 minus 1 units in its length. AL equals to 3 minus 1. In the next step, we will join points O and A together by a straight line. Point O is the center of the circle. Point A is the point of the circle itself. Therefore, OA is the radius of the circle. That is R according to our definition. In the next step, I'll copy the right green triangle ALO in a new page, and we will implement on this right green triangle ALO the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the abbreviation for Pythagoras theorem. So actually this is the right triangle A and O that according from the original drawing. This right triangle A and O, according to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AL squared plus LO squared. So I write it down. AO squared, that is the square of the hypotenuse, is equal to AL squared plus LO squared. So AO squared equals to AL squared plus LO squared. AO is R, therefore AO squared is R squared. And it is equals to AL squared. AL is 3 minus R, therefore AL squared is 3 minus R squared. Plus LO squared. LO is square root of 7 minus 2, therefore LO squared is square root of 7 minus 2 squared. So in total we should find out that R squared equals to 3 minus R squared plus 7 minus 2 squared. So R squared equals to 3 minus R squared is 3 squared, that is 9, plus R squared minus 2 times 3 minus R, that is minus 6R, plus square root of 7 minus 2 squared. 7 square root of 7 minus 2 squared is equal to, in total, to 0.417. So in total we have found out that R squared equals to 9 plus R squared minus 6R plus 0.417. So here we have R squared on both sides of this equation, so R squared will get cancelled. After I cancelled R squared on this side of the equation, we left with nothing, that is to say 0. While on the other side of this equation, we have 9 plus 0.417, that is 9.417 minus 6R. So in total, we actually found out that 0 equals to 9.417 minus 6R. Here we add 6R to this equation, and we get that 6R equals to 9.417. Here we divide this equation by 6, and we get that R, this is the radius that we are looking for in this question, is equal to 9.417 over 6. 9.417 over 6 is equal to 1.57 units. So we have found out that the radius that we are looking for in this question, that is the radius of this circle, is equal to 1.57 units in its length. So we finish with the first question. In the next step, I will present to you the second question, and we will solve the second question in 2 different methods. Our task in the second question is to find out the area of this circle. So in the drawing we have a circle. This is line segment BC, this is equals to 6 units in Islam. This is called BA, this is equals to 13 units in Islam. This is line segment CD, this is equals to 18 units in Islam. Those two angles, double right angles. Again, our task is to find out the area of this circle. So first of all, those two right angles, they are defined as one-sided interior angles. Those two right angles are defined as one-sided interior angles. The sum of those two right angles is of course 180 degrees. And according to rule 27, if the sum of two one-sided interior angles is equal to 180 degrees, like here, then they must be located between parallel lines. So according to rule 27, chord BA must be parallel to line segment CD. So chord BA is parallel to chord CD. Why? Because the sum of those two one-sided triangles is equal to 180 degrees. So when it's done, we should know that chord BA is parallel to line segment CD according to rule 27. In the next step, we will define the center of this circle. This point is point O. And from point O, that is the center of the circle, we will draw perpendicular on line segment CD. Again, from point O, we will draw perpendicular on line segment CD. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O in line segment CD. This point is point M. In the next step, we will extend the perpendicular. We will extend the perpendicular OM by straight line until it touches chord BA. Repeat again. We will extend the perpendicular OM by straight line until it touches chord BA. And we will define the touching point of the extended perpendicular OM with chord BA. This point is point N. So from point O, that is the center of the circle, we have perpendicular OM on line segment CD. We extended the perpendicular OM by straight line. In this way, we created line segment ON. Because of the fact that CD is parallel to BA, it means that the extended perpendicular OM, that is ON, must be also perpendicular to chord BA. Why? Because if you have two parallel lines, for example, we have here this is line A, this is line B, and we know that line A is parallel to line B. And from this point, we will draw perpendicular on line A. And we extend the perpendicular by straight line until it touches line B. Then it will be also perpendicular on line B. Why? Because line A is parallel to line B. So here, from point O, we have perpendicular OM. We extended the perpendicular OM by straight line. Therefore, ON must be also perpendicular on chord BA, to chord BA. So here, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to what I will explain to you. So by doing this construction, we're going to do quadrilateral BCMN. Inside quadrilateral BCMN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this 4 pieces angle must be equal to 90 degrees in its size. So in quadrilateral BCMN we have 4 right angles. Therefore, according to rule 5, quadrilateral BCMN is a rectangle because it has 4 right angles. ON is perpendicular to chord BA, therefore it is absolutely a straight line. So if we focus on the lower side of the straight line ON at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the lower side of the straight line ON at point M? We have this angle that is 90 degrees according to our construction, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will do another construction. That is to say, from this point A, we will do perpendicular on CD. Again, from point A, we will do perpendicular on CD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. When you find the touching point of the perpendicular from point A and isometh CD, this point is point L. By doing this construction, we're going to do the lower quadrilateral NMLA. Inside the lower quadrilateral MNLA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4 pieces angle must be equal to 90 degrees in its size. So inside quadrilateral NMLA we have 4 right angles, and therefore according to rule 5, quadrilateral MNLA is a rectangle. So that is done. In conclusion, we found out that both those two quadrilaterals are rectangles. So here we can implement rule 19. We can click here on rule 19 and we implement rule 19 in our drawing. According to rule 19, the perpendicular from the center of a circle towards any chord bisect the chord. So in the drawing we have a circle, point O is the center of the circle, AB is the chord in this circle. So the perpendicular OM on chord AB bisects chord AB. Again, the perpendicular OM on chord AB bisects chord AB. So according to rule 19, the perpendicular from the center of the circle towards any chord, bisect the chord. You can implement rule 19 in our drawing, because in our drawing we have from the center of this circle, that is to say from point O, we have perpendicular ON on chord BA. Again, from the center of the circle, that is to say from point O, this point O, we have perpendicular ON on chord BA. And according to rule 19, perpendicular ON bisects chord BA. That is to say, perpendicular ON divides chord BA into two halves. BA in total equals to 13, therefore the first half must be equal to 13 over 2, that is 6.5. And the second half must be also equal to 13 over 2, that is 6.5. We already found out that on the other BCMN is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. So rectangle BCMN, side BM must be equal to the opposite side CM, but BM is 6.5, therefore the opposite side CM must be also equal to 6.5 units in its length. Likewise, in the lower rectangle MNLA, side NA must be equal to the opposite side ML, but NA is 6.5, therefore the opposite side ML must be also equal to 6.5 units in its length. What is the length of this missing line segment? Line segment LD. From the drawing it is very easy to see that LD in total equals to CD minus CL. Again, CD minus CL equals to LD. So write it down. LD equals to CD minus CL. So LD equals to CD. CD is 18 according to what is given in the question. Minus CL. CL in total equals to 6.5 plus 6.5, that is 13. So in total I should find out that LD equals to 18 minus 13, that is 5. So LD equals to 5 units in its length. This is the short line segment LD, that is equals to 5 units in its length. In the next step, we will extend line segment DC by a straight line until it touches the circle. And we will define the touching point of the extended line segment DC with this circle. This point is point T. By doing this construction, we created chord TD. This is chord TD. So now we can implement rule 19 on chord TD. Well, because from the center of the circle, that is to say from point O, we have perpendicular OM on chord TD. Again, from the center of the circle, that is point O, we have perpendicular OM on chord TD. And according to rule 19, perpendicular OM bisects chord TD. That is to say, it divides chord TD into two halves. The first half is TM, the second half is MD, and of course TM equals to MD. So write it down. According to rule 19, TM equals to MD. at MD in total equals to 6.5 plus 5. This is 11.5. So we can argue that MD equals to 11.5 units in its length. And from this equation, Tm equals to Md equals to 11.5. We derive that Tm is also equals to 11.5 units in its length. So from one side, Tm equals to 11.5. But from the other side, Tm also equals to Tc plus Cm. Again, Tm equals to Tc plus Cm. So from the other side, Tm equals to Tc plus Cm. And from this equation, we will derive that 11.5 equals to Tc plus Cm. So 11.5 equals to Tc. Tc is the missing sign, so we leave Tc. It is plus Cm. Cm is 6.5. Therefore, we substitute Cm by 6.5, and we get that 11.5 equals to Tc plus 6.5. Here we subtract 6.5 from this equation, and we get that the missing 97 Tc is equal to 11.5 on 6.5 is 5. So Tc equals to 5 units in its length. This is 97 Tc. This is equals to 5 units in its length. In the next step, we'll extend line 7 BC by straight line until it touches the circle. And we will define the touching point of the extended line 7 BC with this circle. This point is point Q. By doing this construction, we can deduce called BQ. This is called BQ, and called BQ intersects with called TD at point C. Again, called BQ intersects with called TD at point C. So write it down. Called BQ intersects with chord TD at point C. The intersection point occurs at point C, this point. And again, if you found out that chord BQ intersects with chord TD at point C. So here we can implement rule 15. So effectively on rule 15, according to rule 15, if chord AB intersects with chord CD at point O, then the following equation is true, that AO times OB equals to CO times OD. So in the domain you have a second, this is called AB, that intersects with chord CD at point O. So in this domain, the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So whenever two chords intersect with each other, we can implement rule 15. In our drawing, we only found out that chord BQ intersects with chord TD at point C. So all the requirements of rule 15 are satisfied, and therefore we can implement here rule 15. According to rule 15, the following equation is true, that Tc times CD equals to BC times CQ. Again, TC times CD equals to BC times CQ. So write it down. TC times CD equals to BC times CQ. Okay, again, according to rule 15, the following equation is true. That TC times CD equals to BC times CQ. TC is 5 times CD. CD is 18 according to what is given in the question, and it is equals to BC. BC is 6, also according to what is given in the question, times CQ. CQ is the missing sign, so it is. So in total, if we found out that 5 times 18 equals to 6 times CQ. Here we will divide this equation by 6, and we get that CQ, let me see, now CQ is equal to 18 over 6 is 3, and 3 times 5 is 15. So CQ equals to 15 units in its length. This is 97 CQ, that equals to 15 units in its length. So in the drawing, we have here, this is peripheral QBA. This is peripheral QBA, and peripheral QBA equals to 90 degrees in size according to what is given us a question. So in the next step, we join points Q and A together by a straight line. So we join points Q and A together by a straight line. So in the drawing, we have peripheral angle QBA, this is equal to 90 degrees in size, and peripheral QBA subtend on chord QA. Again, peripheral angle QBA subtend on chord QA. So here we can implement rule 5. Repeat quickly rule 5, according to rule 5. Any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. So in the drawing, we have a circle. This is peripheral angle MAN, that is equal to 90 degrees in size, and for according to this rule 5, peripheral angle MAN must be equal to therefore, according to this rule 5, peripheral angle MAN must subtend on the diameter of the circle. And indeed, peripheral angle MAN subtend on MN, that is the diameter of the circle. So according to this rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. So we can implement rule 5 in our drawing. In our drawing, we have peripheral angle QBA, this is equal to 90 degrees in size, and therefore according to rule 5, peripheral angle QBA must subtend on the diameter of the circle. Peripheral angle QBA subtend on QA, therefore according to rule 5, QA is the diameter of the circle. So I did not, if you found out that according to rule 5, chord QA is the diameter of the circle. But we also know that the diameter of any circle is twice as long as the radius. So if we define the radius of this circle as r, then the diameter QA must be equal to 2r. QA equals to 2r. So the diameter QA is equal to 2R units in its length. In the next step, I'll copy the right big triangle QBA in the new pattern. We will implement the Pythagoras theorem on this right big triangle QBA. This is side BQ, this is equals to 6 plus 15, that is 21. This is side B8, this is equals to 13 units in its length, according to what is given as the question, that, and the diameter QA is equal to 2R. Is also, and the hypotenuse QA of the right triangle QBA is equal to 2R. It is also the diameter of this circle. So I copy the right triangle QBA in the pattern. We will implement on it the Pythagoras theorem. So here, this is the right triangle QBA, that is copy from the original drawing. This right triangle QBA, according to the Pythagoras theorem, QA squared, that is the square of the hypotenuse, equals to QB squared plus BA squared. So I write it down. QA squared, that is the square of the hypotenuse, equals to QB squared plus BA squared. The hypotenuse QA equals to 2R, therefore QA squared is 2R squared, that is 4R squared. And it is equals to QB squared. QB is 21, therefore QB squared is 21 squared, that is 441. Plus BA squared. BA is 13, therefore BA squared is 13 squared, that is 169. So in total, we found out that 4R squared equals to 441 plus 169, so 4R squared equals to 441 plus 169 is 610. So 4R squared equals to 610. Here we divide this equation by 4, and when we get that R squared equals to 610 over 4 is 152.5. So R squared equals to 152.5. Our task is to find out the area of this circle. So actually we know that the area of any circle is equal to pi times the radius of the circle squared. And therefore the area of our circle must be equal to pi times the radius of our circle squared. We already found out that the radius of our circle squared is r squared. So the area of our circle must be equal to pi r squared. So it is pi times r squared. But we already found out that r squared equals to 152.5. So we solve r squared this expression by 152.5. And again that the area of this circle is equal to either 152.5 times pi squared is inside. So in terms of numbers, the area of this circle is equal to 479.09 square units in its size. Repeat again, we should found out that the area that we're looking for in this question, that the area of this circle is equal to either 152.5 times pi square units in size. So in terms of numbers, the area of this circle equals to 479.09 square units in size. So we finish with the first method. In the next step, I present to you how to find out the area of this circle according to the second method. In the second method, we will use some of the things that we already found out in the first method. In the first method, we already found out that this is 970C, this is equal to 5 units in its length. This is 970Q, this is equal to 15 units in its length. So we use those two things that we already found out in the first method. So in the drawing we have, this is called BQ, that intersects with called TD at 90 degrees. This angle is right angle. And the second point occurs at point C. So whenever you have two chords that intersect with each other at 90 degrees, like here, you can implement rule 26. Therefore, we will implement rule 26 in our drawing. So repeat quickly rule 26. First of all, rule 26 is true in any circle. So in any circle, if two chords, that is to say chord AB and chord CD, intersects with each other at a right angle, chord AB intersects with chord CD at 90 degrees. They create with each other 90 degrees at their intersection point at this point O. So we have here two chords that intersect with each other at 90 degrees. So in this drawing, the following equation is true, that AO square plus OB square plus CO square plus OD square equals to 4R square, and R is the radius of this circle. Again, whenever you have two chords that intersect with each other at the right angle, like here, chord AB intersects with chord CD at 90 degrees, then the following equation is true, that AO square plus OB square plus CO square plus OD square equals to 4R square, and R is the radius of the circle. So we can definitely implement rule 26 in our drawing. In our drawing we have chord TD that intersects with chord BQ at 90 degrees at point C. Again, chord TD intersects with chord BQ at 90 degrees at point C. So all the requirements of rule 26 are satisfied, and therefore we can implement here rule 26. So I write it down. We should find out that in our drawing, chord TD intersects with chord BQ at 90 degrees, and there the second point that is point C, they get between them with each other 90 degrees. This angle equals to 90 degrees in size. So chord TD intersects with chord BQ at 90 degrees, and the intersection point occurs at this point, point C. But again, in our drawing, we have chord TD intersects with chord BQ at 90 degrees at point C. So all the requirements of Rule 26 are satisfied, and therefore we can implement Rule 26. According to Rule 26, the following equation is true that TC squared plus CD squared plus BC squared plus CQ squared equals to 4R squared, and R is the radius of this circle. And again, according to Rule 26, the following equation is true. The TC squared plus CD squared plus BC squared plus CQ squared equals to 4R squared. TC is 5, therefore TC squared is 5 squared, that is 25. Plus CD squared. CD is 18 according to what is given in the question, therefore CD squared is 18 squared, that is 324. Plus BC squared. BC is 6, therefore BC squared is 6 squared, that is 36. Plus CQ squared. CQ is 15, therefore CQ squared is 15 squared, that is 225. And it is equal to 4R squared. So in total, we should find out that according to Rule 26, 25 plus 324 plus 36 plus 225 equals to 4R squared. 25 plus 225 is 250. So we have 250. And 324 plus 36 is 360. So 250 plus 360 equals to 4R squared. 150 plus 360 is 610, so 610 equals to 4R squared. Here we divide this equation by 4, finding again that R squared equals to 610 over 4 is 152.5. So R squared equals to 152.5. Our task is to find out the area of this circle. So actually we know that the area of any circle is equal to pi times the radius of the circle squared. Because again, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. But we already found out that the radius of our circle squared is R squared. So the area of our circle must be equal to pi times R squared. But we already found out that R squared equals to 152.5. So we solve R squared in this expression by 152.5, and in total we get that the area that we are looking for in this question, that is the area of this circle, is equal to pi times 152.5 square units in its size. In terms of numbers, pi times 152.5 is equal to 479.09 square units in its size. So actually, in both methods, we found out actually that the area of this circle equals to either 152.5 times pi square units in its size, or in terms of numbers, the area of this circle equals to 479.09 square units in its size. So we finish with the second method and the second question. In the next step, I will summarize the lecture. We start with the first question, of course. In the first question, our task is to find out the radius of this circle. So in the moment we have a circle, this is the right angle ABC. This is angle ABC, this is right angle. In addition, we know that this is angle ABC, this is right angle. And we know also that side AB of triangle ABC equals to 3 units in its length. This is 97 AD, this is also equals to 4 units in its length. This is 97 DC, this is equals to 1 unit in its length. Again, our test is to find out the radius of this circle. So first of all, we implemented 125 in our drawing. According to 125, if from a common standpoint point P, we will draw a tangent PA to a circle, and also a line segment that is defined as secant PC that cuts the circle at 2 points B and C. Then the following equation is told that PA square equals to PB times PC. Again, PA square equals to PB times PC. So we can implement 125 in our drawing. Why? Because in our drawing, if we focus on this common standpoint point C, from this common standpoint point C, we have tangent CE that is tangent to the secant point E. In addition, we have also secant CA that cuts the circle at 2 points C and A. So all the requirements of Rule 25 are satisfied, and therefore we can implement Rule 25. According to Rule 25, CE square equals to CD times CA. Again, CD square equals to CA times CA. Again, CE square equals to CD times CA. And again, according to Rule 25, the following equation is true that CE square equals to CD times CA. CE is the missing side, so we have to it is. And this is equals to CD. CD is 1 times CA. CA in total equals to 1 plus 3, that is 4. So in total, if you want to know that CE square equals to 1 times 4, that is 4. So CE square equals to 4. Here we took a out of this equation. If I found out that C equals to the square root of 4, that is 2. So the length of this tangent CE is equal to 2 units. In the next step, I copied right angle ABC, and in the page I implemented on this right angle ABC the Pythagoras theorem. The hypotenuse AC is 1 plus 3, that is 4. AB is 3, and BC is the missing side. Okay, this is right angle ABC, this is the comment from the original drawing. This right angle ABC according to the Pythagoras theorem. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. AC is the hypotenuse, so the square of the hypotenuse is AC squared, and AC squared must be equal to AB squared plus BC squared. AC is 4, therefore AC squared is 4 squared, that is 16, plus AB squared. AB is 3, therefore AB squared is 3 squared, that is 9, plus BC squared. BC is the missing side, so leave it as it is. So in total, if you found out that 16 equals to 9 plus BC squared, you have subtracted 9 from this equation. If I found out that 16 minus 9 is 7, so 7 equals to BC squared. Here we took out of this equation. If I found out that BC equals to the square of 7 units in its length. Okay, so this is side BC of the right angle ABC is equals to the square of 7 units in its length. We already found out that AC equals to 2. So what is the length of this line segment BE? BE equals to BC minus 3C. Again, BE equals to BC minus 3C. So BE equals to BC is square root of 7 minus 3C. So AC is 2. So in total, BE equals to the square root of 7 minus 2 units in its length. In the next step, we join points O and D together by straight line. It is given this equation that point O is the center of the circle, point E is the point of the circle itself, therefore OE is the radius of this circle. We define the radius of this circle itself, so OE equals to R. The radius OE that is equals to R, the radius OE is drawn to point E, that is the point of tendency of tangent BC with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius EO. If BC is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to Rule 1. In the next step we did another construction that is to solve from point O, we don't have an angle on AB. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the paragraph from point O inside AB, this point is point L. By doing this construction, we can do quadrangle NOEB. Inside quadrangle NOEB, we have 1, 2, 3 angles. The sum of 3 angles is 270 degrees, so 270 degrees plus the size of this 4 pieces again. Total must be equal to 360 degrees, according to the order. The sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this 4 pieces again must be equal to 90 degrees in size. So inside quadrangle NOEB we have 4 integers, and therefore according to rule 5, quadrangle NOEB is left again because it has 4 integers. But we also know that the opposite sides of left angle are equal to each other. So left angle NOEB side OE must be equal to the opposite side NB, but OE is out, therefore the opposite side NB must be also equal to R. Likewise, according to the sum rule, in the sum of the LOBE, side BE must be equal to the opposite side LO, but BE is equal to 7 minus 2, therefore the opposite side LO must be also equal to the square root of 7 minus 2 units in its name. What is the ref of this missing 970 AN? AN equals to AB minus LB again. AN equals to AB minus LB. AB is 3 minus LB. LB is out, so in total AN equals to 3 minus 1. This is 970 AN, this equals to 3 minus 1. AO, the opponent AO is the diameter of the circle that is R, and side LO equals to the square root of 7 minus 2 units in its name. In the next step I go with the right dimension triangle ANO in a new page and implemented the Pythagoras theorem on this right dimension triangle ANO. So this is the right triangle ANO that according to the original drawing. In this right triangle ANO, according to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AN squared plus NO squared. AO is out, therefore AO squared is R squared, and it is equal to AN squared. AN is 3 minus R, therefore AN squared is 3 minus R squared, plus NO squared. NO is square root of 7 minus 2, therefore AN squared is square root of 7 minus 2 squared, that is 0.417 0.417 units. Okay, again, square root of 7 minus 2 squared, in total it is equal to 0.417. So in conclusion, actually found out that R squared equals to 9R squared. R squared equals to 9 plus R squared minus 6R plus 0.417. We have R squared on both sides of this equation, so R squared we can cancel, we cancel R squared, this side of the equation we left with nothing, that is to say 0, and on the other side of this equation we have 9 plus 0.17, that is 9.417 minus 6R. So in total we found out that 0 equals to 9.417 minus 6R. We added 6R to this equation. And I found out that 6R equals to 9.417. Here we divided this equation by 6 and finally found out that R equals to 9.417 over 6 is 1.57. So in total we found out that the area of this circle, that is the area that we are looking for this question, is equal to 1.57 units in its length. Again, we found out that the radius of this circle, R, is equal to 1.57 units in its length. So if we finish with the first question, in the next step I present you to the second question, and we solve the second question in 2 different methods. In the second question, our task is to find out the area of this circle. So we start with the first method. First of all, in the drawing we have a circle. This is line 7 BC. This is equals to 6 units in its length. This is called B8. This is equals to 14 units in its length. This is line 7 CD. This is equals to 18 units in its length. Those two angles are both right angles. Again, our task is to find out the area of this circle. So first of all, those two angles, now multiply this one-sided interangles. The sum of those two angles is 180 degrees. And according to rule 27, if the sum of two one-sided interangles is equal to 180 degrees, they must be located between parallel lines. The sum of those two one-sided interangles is equal to 180 degrees, and therefore they must be located between parallel lines. That is to say, chord BA is parallel to line 7 CD. Again, BA is parallel to CD according to rule 27. In the next step, we define the center of this angle. This point is point O. And from point O, we go perpendicular on TD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and CD. This point is point M. And in the next step, we extended the perpendicular OM by side line until it touches chord BA. We define the touching point of the extended perpendicular OM with chord BA. This point is point N. So we know that CD is parallel to BA according to rule 27. Therefore, the perpendicular OM, the extended perpendicular OM, must be also perpendicular on BA. Why? Because they are parallel to each other. If you have line A that is parallel to line B, then the perpendicular to A will be also perpendicular to B, because they are parallel to each other. So here, the perpendicular OM will be also perpendicular on BA, because they are parallel to each other. So this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to what I already explained. So here, by doing this construction, you can do quadrilateral BCMN. Inside quadrilateral BCMN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle in total must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this fourth missing angle must be equal to 90 degrees in size. So in quadrilateral BCMN, we have 4 right angles, and therefore, according to rule 5, quadrilateral BCMN is a right angle. ON is a perpendicular, it is absolutely a straight line. So if you focus on the lower side of the straight line ON at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles from one side of a straight line is equal to 180 degrees. So in angles here at the lower side of ON at point M, we have this angle that is the right angle according to our construction, plus this missing angle, so that the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in size. In the next step, we did another construction, that is to say, from point A, we do perpendicular on CD. Again, from point A, we do perpendicular on CD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and line 7 CD. This point is point L. When doing this construction, you can do the lower quadrilateral MNLA. Inside the lower quadrilateral MNLA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total, they must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside polygonal MNLA we have 4 rectangles, and therefore according to rule 5, polygonal MNLA is a rectangle. So in conclusion, if we found out that those two polygonals, they are both rectangles. Here we can implement rule 19, where from the center of the circle, that is to say from point O, we have perpendicular ON on chord BA. Again, from point O, that is the center of the circle, we have perpendicular ON on chord BA. And according to rule 19, the perpendicular from the center of the circle towards any chord bisect the chords. So the perpendicular ON from the center of the circle, that is to say from point O, bisects chord BA. BA in total equals to 13, therefore each half must be equal to 13 over 2, that is 6.5. So the first half BN is 6.5, the second half NA is also 6.5. So we know that BCMN is a rectangle and the opposite sides of a rectangle are equal to each other. So in rectangle BCMN, side BN must be equal to the opposite side CM, but BN is 6.5, therefore the opposite side CM must be also equal to 6.5 units in its length. Likewise, in the lower rectangle MNNA, side NA must be equal to the opposite side ML, but NA is 6.5, therefore the opposite side ML must be also equal to 6.5 units in its length. What is the length from this missing line segment LD? LD equals to CD minus CL. Again, CD minus CL equals to LD. And again, LD equals to CD minus CL. So LD equals to CD, CD is 18, minus CL. CL in total equals to 6.5 plus 6.5, that is 13. So in total, LD equals to 18 minus 14, that is 5. This is the missing line segment LD, that is equals to 5 units in its length. In the next step, we extended line 76 by sideline until it touches the circle. We define the touching point of the extended line 76 with this circle. This point is point T. By doing this construction, we can then chord TD. This is chord TD. From the center of this circle, that is to say from point O, we have perpendicular OM on chord TD. And according to rule 19, perpendicular OM bisects chord TD. If perpendicular OM bisects chord TD, it means that TM equals to MD. According to rule 19, TM equals to MD. But MD in total equals to 6.5 plus 5, that is 11.5. So you can argue that TM equals to DMD. MD equals to 11.5. And for this equation, TM equals to MD equals to 11.5. We derive that TM also equals to 11.5 units in its length. So from one side, TM equals to 11.5. But from the other side, TM also equals to TC plus CM. So from the other side, TM also equals to TC plus CM, and from this equation 11.5 equals to TM equals to TC plus CM, we will derive that 11.5 equals to TC plus CM. So 11.5 equals to TC. TC is the missing sign, so we use TC plus CM. CM is 6.5, therefore we substitute CM here by 6.5. In total, if we found out that 11.5 equals to TC plus 6.5. Here we subtract the 6.5 from this equation, if I found out that 13.970 is equal to 11.5 minus 6.5 is 5. This is the missing 970C. This is equal to 5 units in its length. In the next step, we extended 970BC by sideline until it touches the circle. We define the touching point of the extended 970BC with this circle. This point is point Q. By doing this construction, we're going to do chord BQ that intersects with chord TD at point C. Again, we have chord BQ that intersects with chord TD at point C. So here we can implement rule 15, according to rule 15, you get that TC times CD equals to BC times CQ. You get TC times CD equals to BC times CQ. TC is 5, CD is 18, BC is 6, CQ is everything inside. So in total we should find out that 5 times 18 equals to 6 times CQ. Here we divided this equation by 6 and found out that CQ dimension 97 CQ equals to 18 over 6 is 3 and 3 times 5 is 15. So CQ equals to 15 units in its length. This is the missing side CQ. That is equals to 15 units in its length. So in the drawing we have rectangle QBA. That is equals to 90 degrees in size. We join points Q and A together by start line. So we have rectangle QBA. That is equals to 90 degrees in size. And rectangle QBA subtend on chord QA. Again, rectangle QBA subtend on chord QA. And therefore, according to rule 5, any rectangle that is equals to 90 degrees in size must subtend on the diameter of the circle. So rectangle QBA equals to 90 degrees in size, and therefore it must subtend on the diameter of the circle. Rectangle QBA subtend on chord QA, and therefore, according to rule 5, chord QA must be the diameter of the circle. The diameter of any circle is twice as long as the radius. So if the radius is r, then the diameter QA must be equal to 2r. So in the next step, I copied the right triangle QBA in the new page and implemented the Pythagoras theorem on this right triangle QBA. Q will be equals to 5 plus 16, this is 21. BA equals to 13, and the opposite QA equals to 2r. So this is the right triangle QBA that the point from the original domain. In this right triangle QBA, according to the Pythagoras theorem, QA squared, that is the square of the opposite, equals to QB squared plus BA squared. QA is 2r, therefore QA squared is 2r squared, that is 4r squared, and it is equals to QB squared. QB is 21, therefore QB squared is 21 squared, that is 441, plus BA squared. BA is 13, therefore BA squared is 14 squared, that is 169. So in total, if you found out that 4r squared equals to 441 plus 169. 441 plus 169 is 610. So in total, if you found out that 4r squared equals to 610, here we divided this equation by 4 and found out that r squared equals to 610 over 5 is 152.5. So in total, if you found out that r squared equals to 152.5. Our test is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared, and therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is r squared, so the area of our circle must be equal to pi r squared. But r squared is 152.5, so we substitute r squared by 152.5, and finally found out that the area of our circle is equal to either 152.5 pi squared is inside, so in terms of numbers, the area of this circle equals to 479.09 square units in size. We finish with the first method. In the next step, I present to you how to find out the area of the circle according to the second method. In the second method, used with some of the things that we have already found out in the first method. In the first method, we only found out that this is line 17C, this is equals to 5 units in itself. This is line 17Q, that is equals to 15 units in itself. So we use those two things in the second method. So in the drawing we have chord BQ that intersects with chord TD at 90 degrees at point C. And therefore we can implement here rule 25. Whenever you have two chords that intersect with each other at 90 degrees, you can implement rule 26. According to rule 26, the following equation is true, that TC squared plus CD squared plus BC squared plus CQ squared equals to 4R squared. And R squared, R is the radius of the circle. Again, TC squared plus CD squared plus BC squared plus CQ squared equals to 4R squared. Chord TD intersects with chord BQ at 90 degrees. at point C. So all the requirements of rule 26 are satisfied, and therefore we can implement rule 26. According to rule 26, the following equation is true that TC squared plus CD squared plus VC squared plus CQ squared equals to 4R squared. TC is 5, therefore TC squared is 5 squared, that is 25, plus CD squared. CD is 18, therefore CD squared is 18 squared, that is 324, plus BC squared. BC is 6, therefore BC squared is 6 squared, that is 36, plus CQ squared. CQ is 15, therefore CQ squared is 15 squared, that is 225, and it is equal to 4R squared. 25 plus 225 is 250, and 324 plus 36 is 360. So 250 plus 360 equals to 4R squared. 250 plus 360 is 610. So 610 equals to 4R squared. Here we divided this equation by 4 and finally found out that R squared equals to 152.5. Our test is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared, and therefore the area of our circle must be equal to pi times the radius of our circle squared. But we already found out that the radius of our circle squared is R squared. Therefore the area of our circle must be equal to pi R squared. But R squared equals to 152.5. So we can substitute R squared here by 152.5. So we substitute R squared by 152.5. I have found out that the area that we are looking for this question, that is the area of this circle, equals to either 152.5 pi square units in size. In terms of numbers, the area of this circle is equal to 479.09 square units in its size. So in both methods, we found out that the area of this circle is equal to either 152.5 pi square units in size, or in terms of numbers, the area of this circle is equal to 479.09 square units in size. Okay, thank you very much.